Okay, this video is about a matrix multiplication, and this is a very important topic. It is a bit counterintuitive, as you would suspect, that why this needs to be defined separately, because can't we just define it the way we define addition? Can't we define it term by term? And the reason is no, it's not a good definition to make. And the reason we define it in a bit difficult way is you'll realize the reason when we look at the applications of matrices. But okay, the first condition that needs to be satisfied when to check whether the multiplication is well defined for two matrices is this. So what you do is you find the dimensions of the first matrix. Let's say the dimensions are p rows, q columns. You find the dimensions of the second matrix. Let's say r rows, s columns. And the multiplication A into B, the matrix multiplication A into B, this exists only when the column of the number of columns of the first matrix is the equal to the number of rows of the second matrix. So if these two numbers are the same, only then is the matrix multiplication defined. Otherwise, you can't multiply these two matrices. I'll give you an example here. I have a matrix 1, 2, 3, 4, 5, 6. The dimensions of these matrix are it has two rows. So it is a two row and it has three columns. So it's a 2 by 3 matrix. And on the other hand, I have a B matrix which has three rows and it has two columns. So if I were to multiply these two matrices, first I need to check that the number of columns here, that is 3 here, is equal to the number of rows here. So 3 here. So if that is the case, only then I can talk about its multiplication. So yes, 3 here is equal to 3 here. So I can talk about its multiplication. So I can talk about A into B. So a good way to do this is first write the two matrices side by side. So if I have 1, 2, 3, 4, 5, 6, and then I have the B matrix 0, minus 1, 1, 2, 1, 0. So the size of the resultant will be the other two dimensions, the ones which were not in between. So the outer dimension. So this dimension into this dimension. So the resultant will be a 2 by 2 matrix. So if I were to write it like this, it will be a 2 by 2 matrix. And its entries, I'll let you know what the entries are in a bit, but this is the resultant matrix. It will be of dimension 2 by 2, and the way you find its entries is using something called the dot product, or something called the sum product. So what you do is you take the first row of the first matrix and the first column of the second matrix, and you do multiplication term by term. So you multiply 1 with 0, 2 by 1, and 3 by 1, and then you add those results. So if you do the if you were to find the result, you would do 1 into 0, which is just 0, 2 into 1, which is just 2, 3 into 1, which is just 3. And if I were to add these, I would get a 5, right? So my first entry here is 5. And you do this similarly for the other entries. For this entry, this is the first row, second column entry. So I would take the first row from here and the second column from here. So if I take the first row and multiply it with the second column here, this is 1 multiplied by a negative 1. So that will give me a negative 1. A 2 multiplied by 2 gives you a 4. And a 3 multiplied by 0 gives you a 0. So, and if I were to add these entries, these numbers, I would get a 3 here. So that's my entry here. This is 3. Same for the next entry. This is the second row, first column entry. So I would take the second row from here and the first column from here. So if I take a 4, 5, 6, multiply by 0, 1, 1, I would get a 4 into 0, which is 0. A 5 into 1 is a 5. 6 into 1 is a 6. And if I were to find the sum of these numbers, it's 11. So this entry is 11. And lastly, this is the second row, second column entry. So if I were to take the second row here and the second column here, the result would be 4 into minus 1, which is a minus 4. 5 into 2 is a 10, positive 10. And 6 into 0 is a 0. So if I were to find the sum of these numbers, it would be 6. So this entry would be 6. And this is the result. This is the matrix multiplication of these two matrices. It's a 2 by 2 matrix with these entries. Let's do another example. Let's look at this matrices. This is a 3 by 3 matrix, 3 rows, 3 columns. This is also a 3 by 3 matrix, 3 rows, 3 columns, but the most important fact is that the number of columns here is equal to the number of rows here. So matrix multiplication is well defined, and so I can actually talk about x into y. So if I were to write the three matrices side by side, it would look something like this: 1, -1, 1, 0, 0, 2, 3, 1, 0. This is the x matrix, and this is the y matrix: 2, 3, 0, 4, -2, 1, 0, 1, 1. So since the number of columns here is equal to the number of rows here, the matrix multiplication is well defined, and the resultant matrix will have the dimensions of the other two numbers. So it will be a 3 by 3 matrix here. So if I were to take the product here, let's say the final product comes here, it will be a 3 by 3 matrix. And the way you find the entries is the same way that we did over here, the earlier. So what you do is, for this is the first row, first column entry. So you take the first row from here and the first column from here, and then you multiply each and every entry. So 1 multiplied by 2 gives you 2. -1 multiplied by 4 gives you a -4. And a 1 multiplied by 0 gives you a 0. So when you add these and these numbers, you get a -2. So this entry is a -2. Next, this is the first row, second column entry. So I would take the first row and second column from here. So if I multiply 1 with a 3, I get a 3. If I multiply -1 with a -2, gives you a +2. 1 multiplied by 1 gives you a 1. And yeah, this is the sum here gives you 6. So this entry is 6. For this entry, I need the first row and the third column. So first row from here and the third column from here. So if I were to multiply 1 with 0, I would get a 0. -1 once is a -1 times. 1 times is just 1. And if I were to take the sum, this is 0. So this entry is 0. Next, this entry is of the second row, first column entry. So I would take the second row from here and the first column from here. So let's do this. 0 times 2 is 0. 0 times 4 is 0. And 2 times 0 is 0. So these are 3 zeros giving you a 0 as the sum. Next entry is the second row and the second column. So if I were to take the second row here and the second column here, this would be 0 times 3 is 0. 0 times -2 is 0. And 2 times 1 is 2. So this is just 2. The sum is 2. This is second row, third column entry. So I will take the second row and the third column. Multiply 0 times 0 is 0. 0 times 1 is 0. And 2 times 1 is just 2. And so the final entry is 2. This is the third row, first column entry. So I will take the third row from here and the first column from here. 3 times 2 is 6. 1 times 4 is 4. And 0 times 0 is 0. The sum is 10. This is the third row entry, second column. Third row, second column. So I will take the third row and the second column here. This is 3 times 3 is 9. 1 times -2 is -2. And 0 times 1 is 0, which gives you a sum of 7. So this entry is 7. Finally, this is the third row, third column entry. This gives you 3 times 0 is 0. 1 times 1 is 1. And 0 times 1 is 0. The sum comes out to be 1. So this is the resultant matrix. If you have this 3 by 3 matrix multiplied by this 3 by 3 matrix, the result is this 3 by 3 matrix. And before ending this video, one thing I would suggest is for this example, I want you to find what y into x is as well. And because first of all, is this well defined? Yes, this is well defined because this is a 3 by 3 matrix, y is a 3 by 3 matrix, and x is a 3 by 3 matrix. So the number of columns here is equal to the number of rows, and the resultant will be again a 3 by 3 matrix because it is the outer dimensions. And one thing you'll realize is that this y into x doesn't come out to be equal to x into y, and this is one of the important realizations here. So when you have matrices A and B, so when you take the product and when you take the product in the reverse format, first of all, the product in the reverse way may not even exist, but let's say for now it exists. So in general, you can't say that these two things are equal. So this may sometimes come out to be equal, but most of the scenarios, this doesn't come out to be the same matrices. So this is an important realization. This is something which we have been taking for granted. This is usually called the commutative property. While dealing with numbers, we say that x into y is as good as y into x, right? It doesn't matter which way you multiply numbers, but here you realize the fact that it matters in which way you multiply matrices because it might give you different results. So the order matters here. All the other properties, for example, the associative property is satisfied by matrices. If you have A, B, C, three matrices being multiplied, it doesn't matter whether you do B and C first in that order and then you do A with the result, or you do A with B and then you multiply the result with C. It is equal. So this is equal. This is the associative property, which is held by the matrices, and there are a bunch of other properties which are held by which matrices hold. But this is one important property which is not true. In general, this is not true. Sometimes it may be true.